Hi, Algebra 2 students, and welcome to another video lesson. To wrap up kind of what we talked about in class, we looked at a situation involving medication where eventually our sequence ended up leveling off. It reached what we call long-run value, or just to put out a little calculus word for the future, a limit. Okay, and so I just listed here the recursive formula for the sequence we were looking at involving the medication where we were given a 20 milligram dose, I believe, and then we lost 25% of that over the course of a day. And then at the end of the day, we added a 10 milligram tablet, so increased the dose again. Eventually, that leveled off at 40. And remember that in class, we found that out by going to the calculator, typing in that first term, and then letting our calculator kind of use the recursive rule. So taking the previous value and multiplying it by 0.75, and then adding 10. And then remember, the calculator will continue doing that if we keep pressing enter. And initially, you might have been surprised because they were growing the values, the amount of medication in the bloodstream, but eventually it did level off. And depending on what your calculator is rounded to, mine's rounded to 4 decimal places, you could keep clicking. Eventually, it's going to tell you that you reached 40, but if I actually go back up and grab that and copy that down, that number is not really technically 40 yet. In fact, it would always only round to 40. You never quite get to 40. So that was one way of finding the long run value, was to use the calculator. However, we want to be able to find an algebraic way, because there's a sensible way that we can find that if we just think about it a little bit. So one thing I did is I actually put this sequence into my calculator, and I'm not going to actually teach you how to do this at any point in time, but you can. We're going to learn about graphs of sequences in our next lesson. But if you take a look, these are the different terms that were being generated by my calculator, over on this screen here where I was generating those and then plotting those. And we see that there's a level of increase in that sequence, but eventually we have this leveling off. So this is one thing we want to kind of look at, is that in the long run, those terms level off. And we can see that by looking also at a table. So I'm going to open up the table real quick, where initially we had some growth, from 20 to 25 and then to 28.75. But these are the values that our calculator was generating, and eventually they do level off. So what I want to do is I'm going to take that table away, and I'm going to screen capture here. I'm not sure how to do that without opening my tablet. Let's see if I can do that. Screen capture here. I'm going to capture this, and I'm going to grab it and copy it and bring it into our notes. Okay, and this is going to kind of help me show you what's going on. So let me just work with this a little bit to get it formatted the way that we want so we can see it. I should have had that maybe done ahead of time. Okay, so this is the graph of that sequence showing all of those different terms. And what I want to do is kind of key in on what I'm going to call consecutive terms. So points that are right next to each other. So if we kind of look here in the grid, I'm going to just circle a couple of points. And I don't know if it's going to let me write on that. But if we look at those, it ends up being that those two, coordinates here, those values, those outputs, those terms in the sequence consecutive are approximately equal. Okay, and that's important because if we take any of them, let's say that this term here is u sub n, then this term before it would be what we call u sub n minus 1. So any term in its previous term, if that sequence ends up leveling out, has a special relationship, and it's that those two things are actually approximately equal to each other. Not exactly, but approximately, to the point where they're so close that they almost could be considered equal. Well, that's really helpful, because if we take a look at the recursive rule from the recursive formula and write that down, so m sub n equals 0.75 m sub n minus 1 plus 10. And here my u is really my m. We're saying that in the long run, if this levels off, these two things are approximately equal. So if two things are equal, we can call them the same thing. Let's call them both x. And so I'm going to bring in a variable called x, which is representing the long run value of my sequence, and I'm going to replace term and previous term by x because we said in the long run those are approximately equal. And that gives us a nice simple linear equation that we can quickly solve. And the solving steps here, it may not be so clear, but if you've got variables on both sides, let's get all variables to one side. So I'm going to subtract 0.75x from each side, and that will give me 0.25x equals 10. And then if I take that and divide each side by 0.25, I find out that my long run value is exactly what we said it should be, or what we found using our calculator, x equals 40. So it turns out, I think this will be a much quicker way for us, as well as having some algebraic background to it that makes sense to us. Because like we said, and I know over here I had some trouble writing on that screen capture, that if you look at consecutive terms, they are approximately equal. So in the recursive formula, we always have consecutive terms. So if we called them both the same thing, that allowed us to solve for the long run value. So the rest of this video is just putting that into practice. There's going to be one little twist though. So let's look at the first example together. So here is a sequence. And again, we don't know, and we're not going to use our calculator this time, but if there is a long run value, that would mean that these two things, term and previous term, should be approximately equal. So I'm going to go ahead and set them equal to the same thing. I'm going to define my variable, and you can use the abbreviation LRV. And I'm going to set up an equation where those two things in the long run are equal. And if I solve this, I end up getting 0.1 times x equals 2. And x divided by a tenth, think about this, x, or 2 divided by a tenth, division is multiplication by a reciprocal. So 2 divided by 1/10 would be 2 times 10. And that would mean that x is 20. So it looks like the long run value of this sequence is 20. So let me go to my calculator just to check this. Okay, so I'm going to put in the first term is 12. Let's come back to my calculator page here. And so if I put in that my first term is 12, and I'm going to hit enter on that. And then the recursive formula said that to find new terms, I would multiply by 0.9 and then add 2, and I'm going to press enter and see if this eventually does level off at 20. And it sure seems like it's headed there. Let's see. And indeed, it pretty much does. It takes a long time, and you can see why that algebraic method will actually be more sound and quicker. The technology can get us there too, but we want to be able to use the algebra to get there. So it works, okay? So what I'd like you to do right now is pause my video here and see if you can try number 2, and then I'm going to go ahead and work it out. So go ahead and pause now. Okay, and let's see how you did. So if x is my long run value, then that means x would be 0.2x plus 25. And so 0.8x is 25. And this one I don't know if I can do without a calculator. X would be 25 divided by 8/10 is 4/5. So I think that would be 25 times 5/4, or 125 over 4. That's the exact value. Now, I think that that's what, 31, let's see, 31 and a quarter maybe, so 31.25. And maybe you checked it in your calculator. I'm going to go ahead and do that again one more time. If I type in the first value of 500, I'm going to multiply that by 0.2 and then add the 25. Let's see if I can get to 31.25 in the long run. Oh, got there really quick this time. And that might be because I was losing so much. If I'm multiplying by 0.2, I'm technically losing 80%. And so that leveled off a little bit quicker, but our algebraic method again worked. Okay, last 2 examples of the day, and go ahead and press pause and practice here, and then I will reveal the answers and we'll have a discussion. So press pause now. Okay, I went ahead and did the work, so I'm going to take this away and show us the work. And something kind of different happened here compared to what we saw before. So taking a look here, again, I define the variable x to be the long run value. I put it in place of term and previous term because we learned that in the long run, those two things, which I'm going to underline here, are equal in the long run if the sequence levels off. And then I just did a quick solve. And so in number 3, I got -40. And number 4, again, I did the same process and I got -20. So that kind of got me thinking the first time I did this, can the long run value be negative? Okay, well, let's try it out. Let's try it out in our calculators here and just make sure. Okay, so if I come to my calculator and I put in my first term, which is 350, and I press enter, and I multiply by 0.25, and then subtract 30, am I going to level off? Well, it sure looks like I'm going down. The sequence is decreasing. And if I keep clicking, yeah, it does level off at -40. So that one definitely looks like it's correct. So number 3, I think the long run value could be -40. And if we think about why that is, if we multiply by 0.25, that means that we're losing 75% of the previous term. And then on top of that, subtracting 30. So I think at some point we could end up subtracting more than we have, and that would put us negative. So that makes sense that that could happen. Okay, let's check number 4 in the calculator. If my first term is 25, and I multiply that by 1.1, and then add on 2, and I keep doing that, wait a second, this sequence is increasing. It's not becoming negative. Does it ever become negative? I'm thinking not, because this keeps increasing without bound. In fact, I think if we kept playing this out forever, it would just keep getting bigger and bigger and bigger and moving closer and closer and closer to infinity. So it turns out our algebraic method here didn't work. So this is invalid work. So how will we know if we can't find the long run value? Well, truth be told, we're going to have to do a little bit of thinking, just like we always do in math. If we take a look at our recursive rule, we should have known right away that this was going to happen, because it doesn't really matter what we start with. We haven't really talked about the first term when we find the long run value, but look at what we do with that previous term in the first case. We multiply it by something bigger than 1. And if you multiply something by something bigger than 1, it's going to get bigger. Okay, that's growth. And then if we add something onto that, it's going to get even bigger than that. So I think the key here is that that common ratio is greater than 1. And if that's the case, there is no long run value. And nobody's going to be able to tell you that. And the algebra will still solve for something, but the value that it solves for is not true. It's not valid. It's not really where we level off. So you need to recognize that if the common ratio is not smaller than 1, the long run value is not going to exist. Okay, so that's one little twist in this process. It seemed like it was so easy to find the long run value, but it doesn't always work. Most times it will, but always look at your ratios, okay? All right, so hope this your homework assignment goes well. You've got some practice for this. Don't forget about the quiz next time over 1.1 to 1.3. I will see you in class again soon. Bye-bye.